Yeah, my name is Jose Nicolas Baene. I work as a geospatial analyst. This is a very introductory workshop for you to get a grasp on geospatial analysis, especially in Python. So I want to review with you a little bit about the agenda. I will tell you very quickly something about me, the objectives of this talk, a little bit of history of geospatial analysis. We'll get deeper onto what the data, how the data looks like, what the coordinate systems for any of you that have already been exposed to geospatial data. Some of these things will sound familiar, and I hope you take something from this talk because yeah, it's a very basic, very introductory talk, but I hope you do enjoy at least the exercise I have prepared. We'll speak some more about data formats, spatial operations, and mapping. So without much more, the agenda will be divided. I want to focus onto this because this is like the main storytelling I want to give you. So coordinate systems and data formats is mostly related to how data is stored and presented. So bear this in mind, because when you are doing a workflow, you start with, well, how's your data stored and what transformations you should do. Then you will move forward to analysis, and this is when spatial operations come handy. Sometimes it's also for data formatting, but especially in analysis, you will use a lot of spatial operations. And then the visualizations using the mapping, cartography, which is very fun, is the last part when you produce a beautiful map and you show it to an audience. So this, I want you to bear in mind this kind of storytelling. So, I don't know why is your picture, sorry. It didn't get updated, but I'm Jose Baene.
We can change our pictures. So you want them to meet me.
Yeah, sorry, I updated it recently, but I guess it didn't get saved in the presentation. So I am a civil engineer. I also have a Master's of Science in Smart Cities and Urban Analytics. I have experience in different areas and in different industries, but from when I started working with data and geospatial, I have mostly been exposed with telecommunications. So kinds of analysis like fiber deployment, prospective markets, a lot of dashboarding. Also, I had some experience developing go-to-market strategies for geospatial software. And overall, I'm a Python martyr, as most of us, because Python is really fun, but also makes you suffer a lot, and especially when you're doing maps. But it's very, very interesting. So the objectives. I want you to set up you very quickly on what's the essentials of geospatial analysis, and build a ground foundation of what we are going to work on. Also, how to deal with this kind of data in Python. We have a variety of software that can deal with geospatial data. I am focusing on Python because it's the most, is the tool that I have used the most in the most recent years. Some about use of vector data, and I will get deeper into what vector data is later. Something very broad about geospatial operations. There is a ton of geospatial operations out there. I will cover the essential ones that I think are essential ones because they have served me the best, but there are a ton of others. And a very little introduction of mapping and cartography. I am not a cartographer, but I have some cues that I think you will find very, very handy. So, as a brief history of geospatial analysis, well, analyzing geographic data or data that is related to a location in the space has been a thing for quite a long time. So we tend to think that this is very recent, but actually we can go back all the way back until Dr. John Snow. Well, not this one. This is how a hero looks. So this is Dr. John Snow, and around 1854 in London, there was a cholera outbreak around Soho. And everyone thought, okay, cholera is transmitted through air, but actually he didn't think that, and he started mapping, and he did this map on cholera cases, on cholera deaths around Soho, and he started noticing that they kind of clustered, and as you can see, these kind of bars are the frequency of the deaths or the cases of cholera, and they started to cluster, like he noticed it, around roughly this point where a water pump was around. So this pump he thought, okay, cholera should be transmitted then by water, probably. They shut down the pump and then the cholera cases stopped. So as you can see, this is a very initial example of how geospatial analysis started working a long time ago. And from then, we have a lot of breakthroughs. We have computers, satellites, we have a broad disponibility of information through GPS, through Landsat. We also had software, specialized software to work with geospatial data. So we have ArcGIS, which is a very important vendor. We have Python, R, we also have web mapping. And I think today we all had some exposure to some kind of web mapping like Google Maps or Waze or Apple Maps or a ton of others that help us relate with the space we live in. And all of those maps require information, and that information has to be stored or has to be formatted in a specific way, or it's stored in a specific way. And nowadays, there are two main formats. There are other formats as well, but there are two main ones, which are, the first one is vector, is what we call vector. So where the features are represented as geometry. So if you remember, or if you think on a geometry class, you have points, lines, and polygons. So they are very well-defined shapes, very well-defined data. And this is mostly used on thematic mapping. So kind of like some of the elections map you can see around, or web mapping, or crime mapping. So you would think about that, or color mapping that you have around. The other kind of data, of the main one, is raster data, which is features represented as a discrete grid. So think about like an image, a photograph, but is georeferenced. So every pixel has a specific value that represents something that you want to tell. And this kind of data is mostly used in natural sciences or weather. So when you're trying to measure temperature around the world, the globe, or around a territory, or wind speeds, or some densities. So this is kind of the data. This is kind of like a very rough difference on how raster versus vector looks like. So on the left, you will have like an image, and you kind of like get the idea. There is a shape there on the cloud. And then vector will be like the boundaries, the specific boundaries. And these have two different ways of storing. So this workshop will be mostly focused on vector data. I will not be talking because you can do a whole other workshop and a whole other field of working with raster data. So if we go into vector a little bit, you know, if you have worked with data, that data usually has a type. You have strings, you have integers, you have floats, you have a variety of types. A geometry is also a type of field. And the Open Geospatial Consortium, which is an open source consortium that dedicates to develop geospatial parameters, they developed this data model, which is called the simple features model. And what simple features are is just taking all of these spatial data and formatting in a specific type. As we had strings, integers, well, we will assign a type to geospatial data. And they have like, I think around 20 types, but these that I am showing you here are the main ones. So we have point, line, string, and polygon, and their respective like multi-version, because you can have multiple polygons at the same time with the same values, multiple line strings. So these are the main ones that you will bump into most of your applications. Of course, maybe you will find some other weird ones, but these are the main ones. I think it covers 90% of the world. And this kind of data is supported by the main, at least open source software provider. So we have QGIS, which is a program, a GIS program to work with geospatial data. Is very good. It's open source, it's free. You can go ahead and download it and play with it a little bit. It has a graphic interface, so it's very easy to work with. We also have PostGIS, which is the spatial extension for Postgres. So this is a SQL-based geospatial analysis that you can do. And we also have GeoPandas, which we will be looking at here, which is I think one of the main geospatial libraries that is available for Python. So some examples just for you to get some sense of how it looks. of vector data. So vector data, for example, line strings, you will use that for roads or rivers or power lines. So in this case, we have a road intersection, and all of the different lanes and the different parts of the road are represented as lines in this case. We also have points, which usually can be specific locations that you want to mark. So restaurants or signals of crossings, like what you see on Google Maps, like this kind of flag, yellow flag, that's a point. But then you also have the polygon, which is boundaries. So usually polygons are used for administrative boundaries, like the countries or municipalities, also by building footprints. So in this case, we have a double kind of representation because we have the point and we also have the polygon. So this is some examples. So now, right now, we're going to move on how data is stored and represented. And we're going to start speaking about, okay, maps are flat, but the Earth is not. And that poses a challenge for us because we're trying to represent something that is 3D into a 2D plane. And that comes with some considerations that you have to have when you're working with data. So for that, we have the coordinate reference systems, which essentially helps you defining allocation of the points on the surface of the Earth. We have two types of coordinate reference systems. One is the geographic one, which is the one that most GPSs work, and that you will find if you look into your data, it comes with latitudes and longitudes. So in this one, the Earth is represented as a sphere or as an spheroid. An spheroid is essentially a sphere that has a different diameter in different in vertical than in horizontal and in depth. So it's kind of oddly shaped. That's because our Earth is not actually a sphere. It's kind of like more like a potato, but we have to approximate it in some sort. So you use a sphere or spheroids. And also the distance, and you have to bear in mind this, when you have a geographic reference systems and you try to measure a distance, it will not be on meters or feet or any linear unit of measure, but rather in degrees. So sometimes when you're working with this, you will bump into issues trying to find out what distance it is. So when you try to go and make this flat, you have to do transformations. And for that, you have to do assumptions that will condition the implementation of your map or your analysis. So usually we use transformations like the cylindrical, which is the one that you can see on the bottom, or the conical, or some things that it's oddly shaped. Sometimes I will show you some that looks like when you peel an orange or something like that. So that will start already modifying your input data. And all the projection systems has an identifier, and we will look into that further around. So the main one, the one I was speaking, the geographic one, is the 4326 or the WJS 84. That's what all of the GPS in the world uses. And now we have the projected one, once we make everything flat, and that you will find that the coordinates are not latitudes and longitudes, rather you have X and Y or easting and northing. So in this case, you have gone from 3D to 2D, and your units of measurement have gone to meters or to feet or to another linear units. This will depend on the transformation that you're applying on the region of the world, and you will have also other transformations, because when you do this, you start losing precision on your analysis. And usually these transformations can only hold one or two properties. And when I speak about properties, usually a map has multiple properties: the area, the direction, the distance. And when you do transformations, you start to getting, okay, this map only holds one of those two areas. And that doesn't sound good, but you will find for each application an appropriate reference system. So when you're trying to do maybe some engineering design for bridges or roads, then you should bear in mind area and direction. Or when a boat is sailing around the world, well, distance or direction is also very important for they don't to get lost. So the takeaway here is that the projection of your data will have deep implications on what you're doing. And in my experience, most of the times when you have something that doesn't match is because you haven't checked your CRS. So this is a message. So I wanted to to show you some of these transformations that I was telling you. So yeah, we have the Mercator projection on the top left. That's the most common one that you will find everywhere. And then we have some other weird ones. I haven't gotten to use any of these because these are for a specific application, but for most mapping, Mercator will be nice. And then depending on where you work, you will find. And I wanted also to show you how this impact on the way, not only you analyze, but also how we perceive our world. So we have a map of the United States with 3 different projections, and you can see how deformed it looked in different ways. So this is why sometimes we tend to think that, for example, Greenland is absolutely huge. Well, it's actually very small, but it's because the way of our maps has shaped our view of the world. And on geospatial data formats, they can come on multiple formats. One of the most common ones is a shapefile, which is used for vector data. This was developed by Esri, and a lot of people on the open source community don't really like this one, but it's the most commonly used. It's actually a bunch of files, which one holds the geometry, another one holds the data, other holds the projection and additional metadata. You also have GeoJSON, which is kind of more recent, is a text-based vector data, is used a lot for web applications. So this is very good, but the files tend to be a little bit bigger because it's all text. For raster data, we have GeoTIFF, which are essentially images that are geo-referenced. So this is used mostly for satellite imagery or aerial imagery that you will be using around. And this is not actually a format, but some vendors like Postgres, Redshift, Snowflake support geometry types. So you have a column that will hold all your geospatial information as well as other fields in your tables in your database system. So always bear in mind the GIS data format, because sometimes a client or someone will tell you, okay, I have a geospatial file, but it will be a PDF or a CAD file. So usually take in mind that. Right now, we can move on to spatial operations. So now that we know how coordinate systems, how data is stored and what projections should we have in mind, we can move on to look a little bit onto spatial operation. As I told you, this is not a comprehensive view on this. So for spatial operations, these are mathematical computations that helps you extract information and insights or data engineer your data in some other way just to get you to answers from your data. So one of the most common ones is the clipping. This is kind of like, think about it like a cookie cutter. You have like your cookie dough and you use your mold to extract the center part. So this is how clipping works. So you have maybe one geography, a very big map, but you only are interested in a very small area. So just extract that part to continue your analysis. Then you have the spatial joining, which I think is the main one or the more structural spatial operation around, because when you have data on an Excel file or on a database, when you have multiple tables, you try to find an index or a unique identifier to match them. But with spatial joining, you don't have that index, but you have location. So you know the 2 data sets may overlap a little bit or completely or in another way. So you want to join them to create a unique data set that will get you answers. And this operation is kind of like the root of other kinds of operations, such as intersections or the clipping also, or the overlay, which is combining everything. Also, buffering is a very powerful tool in which you create areas around your features, around points or lines on polygons, as you can see here on the illustration. And this works because, for example, you want to know the catchment area around public transport station or around some commerce that you want to find out your competition. So you will do a buffer of 500 meters, 1 kilometer, will depend, and then you can do more analysis. So this is also a very powerful. And then this is mostly used on raster, is the interpolation, which works like the interpolations that we'll learn in calculus. You essentially try to find out a point in the space using the points surrounding it. And this is based on, well, in geospatial, you will say everything that's closer is more like that everything that's farther away. So this works kind of like leveraging that principle. So with all of this combined, you can start getting a sense on how to deal with your data and merge stuff to work further and then get more insights. And now for mapping, because I want to move on to the to the workshop very quickly. For mapping, well, making maps is fun, is very, very fun, but maps are very powerful tools because they, as I told you, they shape the way we see the world, and we also can drive decisions from them. So we have a lot of power, a ton of power. So you will always have to be very mindful on how you're building your maps. And first, you have to always think on your audience, how technical they are, what are you wanting to transmit, and shape your data and your map accordingly. You should use always accurate data, and this is not only for mapping, for any analysis you do. Make sure your data is accurate, is representing the reality, so you can shape that. You should use an appropriate projection. I told you before, like, the projection is very important, so you should show data in a way that is mindful of what people is thinking, and that can give a correct sense of the world. This is a specific advice, and is keep the number of symbols and color very simple, because human mind can get confused very quickly, and if you start overloading a map with a ton of stuff, then people won't understand what you're trying to do. And remember that every map and every visualization always has an opinion. And even though I can get some data, and Danny can have other data, and other people can have other data, and we can come up with multiple ways of showing it on a map. So it always has an opinion. So bear in mind that, and make sure that the opinion that you're presenting is what you're intending to do. That's the responsible part that you should do when you have a ton of power. So that's another advice. I wanted to show you very quickly some good maps. Good is a relative term. Maybe it's good for me. Someone can think that is bad, but I will tell you why I think these maps are good. They have a very simple symbology, so they use very, very small count of colors to show the data. They highlight, for example, Hawaii and Alaska, which are areas that usually get forgotten during the map doing, and we shouldn't leave anyone out. The boundaries tell me the states, but also the counties. So this is a very good one. This one is an interactive map, which shows the height around London. I think it's very good because it's very, very simple in the color shading, but also when you're doing interactive mapping, that unlocks another whole part of mapping. So that's all other thing that you have to bear in mind. You have to bear in mind, is my map going to be static? Is going to be interactive? How it's going to deal? Because that will shape how I can deal. And that shows some other bad or not so good ones. For example, the one on the right, they didn't consider that they were going to print it. So of course, maybe in the computer, it looks beautiful, but right now it's telling nothing. So it's totally useless. And the left one, well, we have a ton of points around with numbers. It's hard to get a grasp on what's happening. Or maybe broadly we can see, okay, yeah, the air quality is not so good around China or India, but it's really cluttered, and you cannot get a really good sense of this. So with that, I will go forward with the workshop. I don't know, Danny, if you have shared the.
Yeah, we have well, we have some questions. I don't know if you want to answer them right now or at the end. They are at WUBA, so I'm looking at them. We have 3 questions. I don't know, you want to answer them at the end or right now?
Maybe let's move forward with the workshop, just
okay.
Because of the time, and maybe through the workshop it can be answered, but
Okay, let's go. So
sorry,
I'm going to share with no, it's okay. So I'm going to share with the participants this link to the Google Colab and the data set you host is going to use for the workshop. So please go to the chat so you can have all the resources. There you go. I already
Okay.
said we're gonna start.
So let us know when you have access to the notebook and to the data, download the data to your computer. And when you are in Collab, Collab is this interface that you're looking, just drag the files that you have just downloaded into this left panel, and you will see them here as I am looking at them right now. So they will load automatically. That's as easy as that. And feel free to let us know if you have any issue, and if you don't, well, you already have the collab. You can copy it, you can use it as you wish. So I set it up for you to be able to play with it after the workshop. I think I can start very quickly, very slowly.
I think you can start. For all the attendees, remember this talk is being recorded, and we're going to upload this recording to our Factor YouTube channel. So if you get lost in any of the steps, don't worry. The meeting is being recorded, so you will have the video later on YouTube, so you can reproduce the workshop exactly as Jose is gonna show us.
Yeah, and also the workshop is hard-coded. I wanted to give it more freedom, but since we are short on time, we should go straight to the point. But I will try to explain myself. So this is Collab, which is a collaborative notebook provided by Google. It's very cool for working like we are doing right now. It has Python by default, and we can install libraries and not worry about setting up an entire environment or an entire environment on our computer. So here you will have a reminder of the objectives. These are the same that I mentioned on the presentation. This first cell that you have to run, you can run it by hitting Control Enter. So it's just for installing the required libraries that we are going to be using throughout the workshop. So this is the first one that I'm going to run. You will get a prompt, maybe some warnings, but everything should install correctly. I have tested this multiple times, so yeah, we have a couple of warnings around, but it's nothing to worry about. Then after we have installed them, we have to import them to be able to use them, and to import some specific functionalities also if we want. So then we should run this other cell to import everything. And here I also put a reminder about how simple feature works, how they look like, and we will look deeper into how actually they look like when they are stored in the memory of a computer. That's why we, from this library called Shapely. So if you have experience with Python, Shapely is to GeoPandas as NumPy is to pandas. So it's like kind of like the root, like it's built one on top of the other. If you don't have experience, it doesn't matter. It's just a fun fact. It's just for you to know that you're able to work with Shapely and GeoPandas. So right now here, we want to check how a simple feature looks like. So I have defined a latitude and a longitude, and then store it as a point. As you can see, I am telling it, okay, store this as a simple feature, as a point. So when I run this code, well, nothing happens. But when I print the latitude, well, I have the number, which is a float number. This is regular. But when I print the point, I have a point. So it's already stored as a point in the memory of the computer. Right now, it doesn't tell me much, but I know it's a geospatial data right now. And I have more examples here on, for example, this is a multipoint, and you can see how the syntax starts to change. So for example, here we have this double bracket syntax to define a multipoint. So when I store this and I print it, I have a maybe not so straight line of points, but these are all stored in a single chunk of the memory right now. So we have all of these multipoints, the same for multi-line string. And as you can see, then again, we start to see the modifications on the syntax. And when I print it, we have this line. So, and you're free to edit this and play around. with latitudes and longitudes. You can go to Google Maps and poke around and get those latitudes and longitudes and input here and try to play around if you want to modify it. We can also do polygons. And in this case is a much more complex shape than what we are used. So this is my polygon. And this bit of code, I will explain you a little bit of how it's working. Here we will have a little bit of interactive mapping, but interactive mapping is very, very broad, is very interesting, and it's just an initial part. So here, I'm going to use another library called Volume, which uses Leaflet to plot geospatial information. It's a very powerful tool, it's very interesting. I have set up a very general HTML format. I am calling an icon that you will see later what is it for. And I will declare a pop-up, which is kind of like the window you have when you click something around. And I will start adding my data. So I will add the point that we had before. I will add the multi-point. I will add the multi-line string. As you can see, we are transforming everything to GeoJSON. You remember I spoke that GeoJSON format is widely used for web mapping. So here you can see it, we're doing web mapping. And then after I add everything to my map, after I have my map set up and I have added everything, then I will just view how it looked like. So when I hit Control Enter, you will find that around here, the point was factor office in Bogota. So we are located in a WeWork at the east of Bogota. And you will see we have here, that's what this line does. It takes the image from Twitter. If I click here, it's a very horrible pop-up, but it says WeWork Usaken, which is where we are located. We have both of the lines, if you remember, that I showed you before, the points, but my polygon, where is it? So right here, my polygon looked very small. When I zoom out, it's actually Bogota's airport. So as you can see, we have created some simple features. These are simple features. This is the power of how they are stored and how can we visualize them. And in a very simple manner, like this is a very basic code. And from this, you can go to customize it a ton and you can get very beautiful visualizations. And now, after we have this and we know that this projection is the web Mercator projection, I wanted to show you also, yeah, maps are flat, but the Earth is not. So as I told you, the World Geodetic System, the 4326, is the one that is used on all GPS system and is the most common projection around. The projected version and the one that uses maps like this one, like the interactive one we have here, is the web Mercator or pseudo Mercator, which is 3857. And this has the meters as units, but I wouldn't use this for designing a road because you will get a little of deformation. That for that you will go to local projected system. Just for fun, as a fact, you will see that we have this EPSG code. Oh, sorry, this EPSG. So EPSG code, that means European Petroleum Survey Group. It's not a company, it's an organization that takes care of projection system, of coordinate systems and documents them and makes them available so you can check the parameters, the spheroid. That's a whole science that it's very interesting. So you can check what sphere are they using, how the azimuth, and a ton of parameters they use. You can check multiple of these codes in this web page, which is APSG.io. So for example, if I look here for 4326, this is the one I was telling you. So if you go in, you will see, okay, the unit is degree. This is the horizontal. This is the area that you can apply it to. You have the spheroid, the definition of the spheroid, the authority. Well, you have a lot of information that I don't even know because this is a whole science that is very, very deep into surveying. We can look all others around the world. So I can go back and, for example, there's one for the United States, the 5070. It's a projected system, and they will say, okay, you can only use it here. So you might guess that if you go outside these boundaries, you will get weird results. And you will find here the precision, even by state. As you can see how it varies around the applications. So where you can use it, how you can use it, what it replaces, well, some history. So this web page is very, very valuable to use. And I wanted to show you, so right now we're going to start using GeoPandas, and GeoPandas come with some data already loaded. So we are going to load that layer from GeoPandas and inspect it. This is a world layer. So essentially we have the population, the continent, the name of the country, the ISO coding, GDP information, I don't know up to what date, but GDP, and then the geometry. You remember I told you about our column, the geometry type. So here it is. You will see we have some multi-polygons, which of course, because Fiji are a multiple islands, so you have multiple polygons, but in, for example, Tanzania is just one polygon. So yeah. And we can check the CRS. So GeoPandas work with this command .crs. And here you will have information about CRS. So, okay, is the geographic 2D, is the WJ64, the axis in for the area you've used. You will have information, broad information of your CRS. So we can plot it using the .plot command. And here we have very conventional map of our world. So yeah, this is 4326, nothing weird. And here we can also do reprojections. I can take 4326 and take it to a whole other projection, depending on my application. And here I just wanted to show you. So we use this command to CRS. It seems too simple, but it's very simple there. Okay, from one CRS to the other one. I just input here the code, the 3857, which is the web Mercator. And if I try to print that, to plot that, well, we start getting weird results because of the way it's coded and because of the way it tries to represent the Earth. So you start to having results that you have to deal with. And just as an example, and because of time, I will try to do one more, and I will leave you these examples, and you go and try to plot the world using local. These are local reference systems. So for China, USA, Colombia. So you will get very interesting results. But I wanted to show you this one, which I think looks very cool. If I plot this, this is a CRS for the United States. And it's an equal area projection. It's usually most for their atlases. So that's why you get like the United States in the center and then everything shaped around. But I think this looks very cool. But I think this is the point I wanted to get to. If you start to projecting the data, then everything starts to get a little bit shifted. So key takeaways. Sometimes you need to reproject your data for the analysis. You have to make sure that your units are appropriate for the analysis you're doing. So if you're designing a road, please don't use degrees. And sometimes you don't have a CRS assigned. It's common that you find, so you have to assign it or to research a little bit. So if you see latitudes and longitudes, to say, okay, yeah, this should be 4326, and that's it. So now we're going to go to the fun part, a little bit of analysis, a bit of the data formats, of subsetting the data, doing some geospatial operations, some reprojections, and we have come from setting up, like we have data locally from well, the points that I actually typed, like the multi-polygons and the multi-line string, and then some data that was already available in our library. But right now we're going to load these data sets that I hope everyone was able to load. This data comes from OpenStreetMap, which is a collaborative open source map of the world. It's a very powerful tool. It started like as a side project from some university people and University College of London, and then it grew so big that it's being fed by people all around the world, and you have free geospatial data available from roads, polygons, points. And in here, we're going to use points of interest, a layer that is called points of interest. And we're also going to be using census data, which is provided by DANE, which is Colombian National Statistics Department. So we're going to be using both of them, some geographic references. So this cell here, if you have loaded, like these two are going to be loaded from, well, from your local memory. And then, as you can see, we can also load from a website. So this is the DANE's website. If I run this cell, we will start to get our data loaded from all of these sources. And as a good practice, in the meantime, while this loads, it's always good for you to check the CRS of your data. That's the first thing I usually do when I am working. Just check, okay, is everything in the CRS I need, or in the same CRS at least, to be able to work. So you remember this command that I showed you before. So right here, what I'm going to do is just load, is just check the CRS of all of these layers. So here we have, so for points of interest, which is the data that comes from OpenStreetMap, we have the 4326, which sounds sensible because it's all the world, but these two that come from Colombia's repositories is 4686. So if we check that one here, we'll go 4286. Is the Magna Sirgas, which is the Colombia's reference system. It's all used for all around Colombia. Makes sense also because these are official layers. But in this case, I will reproject them to 4326. I could have done the other way around. It's just, if you want to change it, you can switch it. You know, we are using these two CRS command, and I will save them as new variables. So they are reprojected, and now I want to plot it. So let's take a look at Colombia. Here we have very general Colombia map. We can also, but okay, we have Colombia, but my analysis is going to be focused the most on Bogota. So we want to filter that a little bit, and Colombia has codes for every municipality. So I am going to be using the one that is for Bogota, which is the 11001. I will plot it. So this is how Bogota looks like. It comes from these data sets. It's just now filtered. Also, maybe I want to check my points of interest, how they look like. Usually that's the other part I use. If it's not a ton of data, I try to plot it to get a general sense of how it looks. So here you have it. We have points of interest all around Colombia, and we have the head. We want to check it, but here we don't have the city assigned. And that's when our task, and for this task, I love getting drinks around Bogota. So what I wanted to do is check which parts of Bogota has higher concentrations of bars, of places where I can get a beer. But since I don't know which city corresponds to all of these points, then we will start using the power of geospatial data. And in this case, we're going to start using spatial join. You remember spatial join from the presentation? This is the function on GeoPandas. So what I'm doing here is just adding Bogota data to the points of interest. And when you see it, you will see that right now, after we get this part done, we'll have the points, as you remember, with the name, the class. And right now we have information of which of those are from Bogota. So, okay, we have filtered it, and now this looks like this. So yeah, that's an improvement on our data. I will clean up. This is only for cleaning because we have a ton of columns here that come from the census data. And we'll check the unique classes because I wanted to show you that OpenStreetMap is very comprehensive on data that they have. So you will find a ton of categories here for any analysis you want. If you are not interested on beers, but rather on cinema or pharmacies, you can do it. So I will just filter those categories in this code. And right now we have 4,000 places where I can get a beer around Bogota. And in here, I will use, again, spatial join. But in this case, I'm going to join it to a smaller geography and kind of like transform it. So this first part will just tell me where is it located in my geography. This other part is just a reformatting, as you will do on Excel. And in here, you will add the polygon geography and replace the point geography for the polygon. So this will run. Oh, didn't I transform anything? Okay, this should be okay. And I can plot it. And this is the first map we have done. So we have concentrations. And this is not a good map, but this is our first map. So these, I can sense there is a concentration around here probably, but I don't know the values. But well, we have something, we have the data, so let's start working. And we can give it some love, so we can change the colors. So we have Color Brewer, which is a very important tool, a very nice tool to get colors for maps. Always bear in mind, do your maps colorblind safe. You don't know who is going to watch your map, and that's something about your audience you have to bear in mind. Make it colorblind safe. You can add a legend. We can check the distribution. I handed you some examples on how distributions shape the way you see your data, and we can add some additional layers. I'm going to go very quickly through this. Sorry about that. But for example, let's make a bigger map and just change the color with this boo-poo, which is, I like that one, but maybe you don't like it. You can choose another one. So I just took these 4 letters and replace them here in the C map, the color map. And now we have this map. It starts to look better. Nah, probably not, but we can go. Right now, let's just add a legend. I want to check what these values look like. So, oh, here is my legend. Okay, this dark color is around 50, but still a lot of categories. I don't know, there are a ton of white space. So let's use a shim. From this shim, the natural breaks, which is around here. This tries to cluster data in natural splitted intervals. And right now, okay, this, I think it looks better. And now you have a very simple legend with the categories. But let's say we want to add some edges, some borders to the data. Okay, I want to look actually, okay, right now, start to look better a little bit, or maybe I want to remove them. And then I can add some more data for context and add a base map. So there is this library, which is called Contextily, which helps us to add. But for that, we have to reproject everything to Web Mercator. You remember Web Mercator from what I spoke about above? So I have to reproject everything to that in order to be able to pull the base map for right now. And I pulled some more data, which are localidad, which is an administrative boundary for Bogota. And right now we're getting a nice map, I hope, with the boundaries. And this last one, okay, here you have it. So right now we have a beautiful base map and all of these boundaries, and I can get a sense, okay, this is the area I want to visit probably after this talk. I don't know, probably it's Tuesday. And this last one is just for adding names, and I wanted to show you, like with Python, you can do a ton of stuff, which is very interesting, but also it can make you suffer. So I want to add the names of the localidades, and I have to create all of this code just for that. And it will look nice, but it will make you suffer. So if I run this code, you will have. And with that, I am wrapping up the workshop. I hope you get a good sense on what can you do. This was very quickly. There's a ton of stuff you can do with Geospatial. This is where I was talking about. So for people that maybe don't have more context about Bogota, well, they know this is called Usaquén, Chapinero, and you got some very cool names, very good maps. And I hope you got a good sense of the basic of Geospatial, on what you can do. And I'm happy to answer any question you have right now. So thank you very much for your attention.